Hello, I hope you can hear me. Let's see. Hi. Okay, it's working. So then I have a textbook here. Oh, I think this, you know, one thing, this is important, I think. I think this book should say this first. A particle that was at x at the time t equals 0 is called particle x. So you have, this is material coordinate, right? x1, x2, then there is this particle is called x. The position is given by x vector. And there is another particle, for example here, you can call this x1, then maybe this position is x1 vector. Okay. So this position in material coordinate specify the particle. That is one thing I think we should remember from the beginning. Another one is this. I have a message from Professor Na. So, see, so what is the streamline? What is the streamline? And what is a path line? So he said, this is very important. Path line focuses on individual particle. Path line focus on individual particle. Streamline overall view of velocity field on the domain. Let me see. You can look at this. Let me start from beginning, okay? Because something in the last chapter we consider initial position x and final position small x of a material particle. Yeah. The motion of the particle from x to small x is a continuous process. Yeah, and this continuity is expressed with the parameter t representing time. Yeah, I think this makes sense, right? This is just a movement of particle. I don't know if we should distinguish this small x and large x, but originally the position is here, right? T equals 0. And this particle moves to another position. So this another position is called x, and this is a function of time. So this is particle x. How particle x move with time. Yeah. So, and this is more ambiguous. So you have, I think you here in this case, this one x1, x2, x3, t is this position. So this position is given. Then you can predict this original initial position. That's this one. So the particle x already moved to position x small x, then the time is t. Yeah? Then you can go back in time. T goes to 0. Then what is the position of particle? That's a large X. Okay, so the material derivative. In the motion of continuous media, the time rate of change of field quantity associated with the material particles play an important role. Very difficult. Let A, the component of a tensor field, be a function of material coordinate x alpha and time t. The material derivative or a substantial derivative of A is defined as this. See, I think this case you have material space which is x1, x2, and we are just considering this particle, right? Then in spatial coordinates, x1, x2, this is particle x. So particle x is sometimes here. Is it particle x? Maybe t equal t1, particle x is here. Then another time, t equal t2, particle x is here. Yeah. Then there is some field, tensor field, Tensor field, what is tensor field? Is something. This is something. The particle x can feel. I think this field is something the particle can feel. Okay, so we are talking about particle x. See? So the something, something the particle x can feel, this change with time. Am I correct? So, and this is the rate. And this is the rate for this change. Yeah, so we are talking about particle x. So, and this particle x can feel something at this position, see, at some time. So, at this position at t equal 1, this one can feel A, t1. Then this same particle x can feel another field. Here, this is A2. Yeah. So then you go to next. If A is a function of spatial coordinates x and t, time t, we have blah blah blah. Yeah, so you have this one, this thing. Strange, huh? This is more like a velocity of particle. This is a velocity of particle x. Yeah. I think you understand this. See, this one, this particle is x when t equal t1, but not x anymore. This particle is not x anymore when t equal t2, right? So this derivative, partial derivative, particle change actually. Particle change, maybe x to x prime or whatever. This is a partial derivative. Yeah, so then you need some complementary term, yeah? Correction term. I would say correction. See, the time derivative of x with the material coordinates fixed is called the velocity of the particle. Yeah, so this is a velocity of particle. I would say x. We are considering particle x. Then with this, for any tensor valued function a, we have this is a nabla. This is a gradient in spatial field. I think at fixed time. I think this is fixed time. So this everything is at given time. Am I correct? Here you can see this is a given time. T is fixed. In the preceding equation, the first term represents the change in A. That is due to the change in time at a fixed spatial position. At a fixed spatial position. The second term represents a change that is due to the change in x with time. This is particle moves. See, because this field is about for this field is for particle x. Yeah. This field, tensor field A, is something particle x can feel. That's a tensor field, right? And this is for particle x. The first term is called the local rate of change, and second term the convective rate of change. Convective rate of changes. Such sums and products of two functions a and b of a. Okay, this is another thing. See, I don't know why they don't change paragraph. This is another thing. See, this is just a mathematic review. See, this is mathematic review. The derivative of sum and the derivative of product obey this. Yeah. So then A, this is again for particle x. For particle x, the acceleration is this. See, interesting. So this one, particle change. The position, spatial position is fixed. So x1, x2, and we are talking about this particle. But this particle change with time. So this particle at t and at t plus delta t, see, originally this was particle x, but then this will change to another particle because this is a spatial coordinate. So it's interesting, right? So how do you calculate? How do you define this one? This is strange. Then this says, okay, V. It's so strange. V. Okay. This V, this is the same V, same V. These V, both V are velocity. This is velocity of particle x. These V are same V, okay? But then if you express this V in terms of small x and t, you have to use this equation to obtain acceleration. Yeah, acceleration. To obtain acceleration, you have to use this equation. But if your velocity is expressed in terms of large x and t, you don't have to worry about second term. You just consider partial v, partial t. This gives acceleration. if we know the mth material derivative, we can find m plus 1th derivative by the relation. This is also mathematical summary. Okay, so don't get confused. This is mathematical summary. So this is separate. So let's think about it. You do a second, no, m plus 1 derivative, right? So you need m's derivative. You have m's derivative and you does partial t. Then you have v dotted with this one. Can you write this is also okay, I think. If you see, if your field, if you write your field in terms of material coordinate and time, then d m plus 1 a dt m plus 1, this is simple, right? You just have d dt, then dm a dtm, this way. Am I making everything clear? So you have like m plus 1th derivative, m plus 1th derivative, you just take derivative of m's derivative again. If a is given as a function of large x and t, so this is no problem. But the complication happens when a is given as a function of spatial coordinate and time, then you have to use this formula. I think this is clearer. Clearer than last time. Yeah. Then we have some terminology. At a spatial point small x, if v equals 0, that point is called stagnation point. See, this is interesting. V equals 0. At that point, this is like a velocity of a particle. This is velocity of particle. Velocity of particle x. Yeah. So this in the material coordinate, spatial coordinate. So this particle stay at this same point. This particle is x. That's called stagnation point. If at a point small x, the velocity v does not explicitly depend on time, that is, v equal v of x the motion is called steady. This is very strange, I think. So here it means like v, you have time, like t1, t2, t3, da da da. And v is same. It says same. Okay. And the spatial position is also same. Spatial position is same position, same position, same position. But the question is particle. Particle may be different, right? x1, x2, x3. That's why this is steady. However, if we express small x in terms of large x and t, we find with, okay, so we use large x instead of small x with t appearing explicitly. Time appears explicitly. What does this mean? I think this is not velocity. Okay, according to, if you follow this textbook carefully, this means this. But I think this shouldn't be a particle. This shouldn't be a particle x. This is like this one. I think this is misleading. This case, this is velocity of particle. Let me see. X. So this seems like a particle change. At each time, particle change. So x doesn't change. Here you can see. Here x doesn't change. X constant. But particle change with time. Yeah, this particle change with time in such a way spatial coordinate doesn't change. So if I read this carefully, this is wrong, This is a velocity of a particle that is at small x at time t. This is a velocity of a particle that is placed at t, at x, at time t. So this is not a velocity of particle large x anymore. A particle that was at x at time t equals 0 is particle x. So this is not velocity of particle x. Let me see. I think this is not a velocity of particle large x. Anyway, stagnation point. This is stagnation point. Path line. A path line is a curve traversed by a particle x as time varies. It has a parametric equation. X, small x equals a function of large x and t. So this is, see? I think t equals 0. At t equals 0, so you just consider spatial field. So there is a particle x, so which is t equals 0. So this particle move with t. That's a path line. This is path line. How a particle x move as a function of time. When a velocity field is given by vi equal vi x comma t, the path line can be obtained by solving the differential system. Very, very strange. Velocity field. This is for same particle. This is for particle x. This is velocity of particle. This one is velocity of particle. Particle large x. This is velocity of particle. figure 6.1, in figure 6.1, the curve on the left shows the path of a particle as time varies. So this is path line. Is it path line? And I would say this is spatial coordinate. This is spatial coordinate. Next, streamline at a given time t, the curve tangential to the velocity vectors are called streamline. So this is just a time t. See, this is very confusing. I would say, I would put time t. I'm sorry, time. This is time t. So you consider, this is different particle. So you consider x1, x2, see, let me see. You have particle x1, which has some velocity, v1, right? So in this way, you move. Maybe you just multiply small time, like dt. So this will give a second position, okay? And at this position, you have another particle, t equal x2. But time is same. Now we are considering time t. This is also time t, same time, same time. Then for particle x2, you have another velocity, vt. Then you multiply small dt. So you get to another point where you find another particle x3. But the time here is the same time. And from x3, you have v3, then you multiply small time dt, then you find another particle, even another particle, which is x4. So this way, you can make some curve, and that's called streamline. Yeah. So streamline at a given time t, the curves tangential to the velocity vector are called streamline. That is, dx is kv. K can be small. This is like time. This is, I think k is small. This has to be small because this is more like dt or delta t. So, but then to eliminate k, you just divide each component. Yeah, so dx1 v1 equal dx2 over v2 equal dx3 over d3. Obviously, at a given time, there is no velocity normal to the streamline. In figure 6.1, the middle diagram shows a streamline with tangential velocity vectors. Okay. Streak lines are curves representing the locus of material particles at time t that would pass through or would have passed through a given point x star. The particle that will be at x star at some time tau is identified as yeah As the parameter tau traverses from the past to the future, we collect all the particles that would ever visit x star. Their location at a particular time t is obtained as x equal x star time at t. I don't understand. Okay, what is the time in this case? Locus of material particles. Strange. I would say, okay, this one, each curve have different tau, maybe. So this is tau 1, this is tau 2, tau 3, and this one tau 4. So you have different tau. But the question is it same particle here, like on this no, local, or how do you call it? Are they same particle? Are they like same particle x1? For tau 2 curve, maybe x2, is it same particle? My question. strict lines are curves representing locus of material particles. What is locus? Ah, trajectory. This is locus is a trajectory. Orbital. Orbital or trajectory. Locus of material particles. At time t, that would pass through or would have passed through a given point x star, the particle that will be at x star at some time tau is identified as, yeah. So I think this local is something like this. So this local is given this way. So then this x star is given as this way. As a parameter t traverses from past to the future, we collect all the particles that would ever visit x star, small x star, their location at a particular time is obtained So we should cut here. In figure 6.1, the curve AB represents the location of particles at time t that would pass through x star at some time along with their path. Okay. Yes, I think I'm right. I think I'm right. So this is different particle. See, you can have this is four particle. You talk about x1, second one. This is x2. This one is x3. This is x4. Right? Then each locus has different type. Tau 1. So this x1, particle x1 is at x star at time tau 1, something like this. So x2, particle x2 is at x star, small x, sorry, x star at tau 2. x3 is at x star at tau 3. x4 is at x star at tau 4. Yeah. Then if you change tau 1, if you change tau from minus infinity to plus infinity, then you can collect all particle. So each tau you have particle. So x, you can also find x infinity minus infinity to x plus infinity. So you should change tau from minus infinity to infinity. You can find a particle x minus infinity to x plus infinity. So you can collect all particle that can pass this point. And this is called a streak line. Material curve. We may express parametrically a contiguous curve of material particle as what do you mean? Contiguous curve. What is contiguous? Continuous and contiguous. We may express parametrically a contiguous curve of material particles as where S is a parameter. This set is called a material curve. I think, okay, here, this is like you can say this alpha is 1, 2, 3, 1, 2, 3, or x, y, z, x, y, z, right? And s is like a index for particle. So x, we can remove alpha, x s1 and x s2. You can say these are different different particles. Yeah. This set is called material curve. So you can say, you can consider material space. So x1 and x2. Then you have some x s1 here, and you can have x s2. So these are different particles. So you can connect different particles contiguously. And this is called material curve. Material curve. Okay. Material surface with two parameters S1 and S2. We may define a material surface. Can you define material surface? S1 and S2. I'm not very sure how you define material surfaces. Yeah, maybe you can define material surface because see you have I need some space. Space, if I can have a space. See, you can have so this is a material coordinate x1 and x2. Then you have x s1 s2. Let me see. Let me do this like t s1 t1. You just move to another point. This may be x s1 t1, right? So then you can move a little bit. Then this new point is like x s2 t1. And this you can also change to another point. This new point is x s2. Sorry, this is t2, right? So then you put another point, even another point. This is the second one. So this is third one is x s3 t1. This point you can change to this end. This end is x s3 t2. Yeah. So in this way, you can make surface. You can make surface. Yeah. I think that's the idea. That is the idea. These material curves and surfaces flow with the motion and occupy spatial curves, and the surface is given by this. So I think this is misprint, right? No, this is okay. This is misprint. You don't need this. XS spatial curves, spatial occupy, spatial curves, and surface is given by. Yes. I think this is easy. So you have spatial coordinate, x1, x2. We were considering only point. Yeah? Okay, so this point at time t, x1, x2, you have this point become this point, right? Because this particle moves. So now we are considering, instead of point, we are considering line, so that this line also at time t, this spatial, this line, material curve uh, at later time become this kind of spatial curve. So if you have some area or surface in material space at later time of t, there is also a surface in spatial coordinate. That's it. Transient spatial curve. An equation of the form fx, t equals 0 describes a spatial curve that changes with time. I'm sorry. Let me take a break here. Okay. So we continue from, is it? What? We go by page, maybe 79. We continue from page 79 next time.